Electronics are all around us. From the computers and cell phones that we rely on for work, school, and pleasure, or in the aircraft, locomotives, and vehicles that get people and goods where they need to go, electronics are there, storing and manipulating data, sensing and operating in the physical world. But how do these electronics get designed? Who conceives of, develops, produces, and tests these components? In this episode, special guests Olivia Puleo and Phil Weigand discuss how modern electronics go from concept to reality. Olivia Puleo is a hardware engineer at Shift5, where she develops embedded hardware and firmware. Her background is in robotics and biomedical engineering, and she enjoys seeing how hardware and software can interact. Phil Weigand is also a hardware engineer at Shift5, where he leads hardware integrations onto platforms like locomotive, aircraft, and ground vehicles. He has lots of experience designing and prototyping electronics in both his personal and professional lives. Olivia, Phil, welcome to the show.
Thank you.
That's nice to be on.
Yeah, well, I am really excited to talk to you guys about designing electronics because as a software engineer, there's this layer of magic that happens once my software gets loaded by a computer or a microcontroller. And it's always fascinating to see electronics go from an idea onto a printed circuit board and something that you can plug in to a battery or a wall or solar panel and see it do these magical things. And what's been so interesting in working with you guys is that seeing that it's not magic, it's actually just another form of engineering with a unique set of skills has been like eye-opening for me. And I'm excited to get you guys on the podcast to talk a little bit about the 101s of designing electronics and putting software onto them to make them do useful work. So maybe we could start, Phil, with a little bit of like what is an electronic device and what kind of components go on an electronic device?
Well, it's a pretty broad field. I'd say, most of us nowadays, though, what we think of electronic devices is far different from, even like 5 or 10 years ago, what might have been the same idea. Because pretty much everything we do today has, integrated, essentially small scale computer systems or low level computational components integrated into everything. So there's still a lot of analog type of electronics that go into making things work, but there is this whole digital factor that where a lot of the times almost everything I'm working on, I need to be working with somebody who's working on the firmware level of the software, basically sort of this integration between when you're going from electrical signals back and forth, crossing back and forth between from that electrical side to the bits. And what is all of this digital logic that you're sometimes running in purely the digital world, and then sometimes it's crossing back over and you're running digital signals through essentially electrical signals. And so there's definitely this cross between it, and essentially getting all of that to work. Work all of it together so you can build something, and then you can get it to the point where you have this finished product that you can then have hand off to somebody, and they can either use directly, or you can hand it off to a high level software engineer, and they can basically take some application they wrote for not that specific system, but just something they coded and run that on this device just like they would any other device.
Yeah, it's a really exciting process. And, when you look at a piece of electronics, oftentimes people will say, well, it's like that green board. And then there's some like little chippy looking things and some, I don't know, plugs and ports and whatever. And so it's really just this like collection of components, of integrated circuits and microcontrollers and sensors and actuators and wiring. And you're designing a system so that it does some sort of useful kind of work, right? So there's the hardware components, which Phil is, I think, where you spend a lot of your time in thinking about how to put these components together to do meaningful work. But Olivia, there's also a whole world of logic and software that goes into these things. Tell me a little bit about where software gets introduced into these electronic devices.
Especially when you're working with these very small embedded type devices, as we tend to do, or as you see in things like your cell phone, your smartwatch, whatever, it gets really hard to distinguish the two fields as you see say a microcontroller, and from the very beginning, we'll sketch out this high level circuit of we want our device to send these messages over whatever peripheral protocol you want, and then plug it into this thing and have it go light up an LED, and for your hello world of electronics is your blinky light. So when you have these things, you have to work really closely with the electrical engineers and draw out, here's how the wires have to go for this. And then immediately after that, here's what digital logic and, sort of firmware software that I need to make those wires do what I need them to do. So it's really hard to pull them apart, which I find fascinating. So,
and it wasn't always that way, right? I mean,
no.
Back in the day, it used to be that like, hey, you are going to take logic gates and this like electronic component is going to do one set of things. It's going to do it well. But now you mentioned microcontrollers. Microcontrollers have kind of opened up a whole new world, right? So Olivia, you spend a lot of your time interacting with these teensy little computers. Tell us a little bit about microcontrollers.
Absolutely. So microcontrollers can come from the very small, simplistic, 8-bit controllers with very little memory on them, and they're fairly limited, and those are, great for their small applications, and you'll see hobbyists use them, and they go up to these, 32-bit microcontrollers that are almost indistinguishable from, some sort of processor. But really, the cool thing about microcontrollers is they have all of these embedded I/O input-output things in order to communicate with all the other devices that, a processor might not. It's really good at thinking, but it's not as good at talking to anything else. So when you have these microcontrollers, you get to go program them, but then you can also go down back to the electrical level, and your programming can say, hey, I want you to pull this voltage high or low, or I want you to, modulate that at a specific frequency and, make a keyboard. That's a fun little maker project that you'll see people do, where you type some keys on your laptop plugged into your microcontroller, and you have a speaker hooked up to it, and all of a sudden you're playing a song with your home row.
So these things are really, microcontrollers are really made so that you have a very customizable integrated circuit on an electronic design that like opens up the world of possibilities to a much greater set of features. And as you said, these microcontrollers are meant to interact with other components on these PCBs, on these printed circuit boards, or these designs. Phil, tell me a little bit about some of the kinds of things that you can put onto a board. What's the world of different kinds of integrated circuits and components that you can have interact with something like a microcontroller to do meaningful work?
Yeah. So one of the interesting things is, step back, a decade or so, and before the microcontrollers really made their advent, you'd be dealing with essentially larger ICs that had maybe some specific logic elements, or even a larger a group of logic elements, basically like a really dumbed down system all on one thing. And then on the other hand, you get things like your processors for computers. And the really nice thing about the microcontrollers, they have, so Olivia was saying, they've got all this input output processor stuff, and unlike the CPU, you don't have to have it has essentially a small portion of RAM built into it, and all these other components all consolidated onto one IC. And this is the kind of thing which is really cool with what we're dealing with now, is just IC technology is really has been advancing at an astounding pace for literally decades now. And so you get all of these really, really advanced components in essentially a single chip. And before, where you had to break it out with a large number of components, you have all of that and grouped into one. And now we're sort of sorting out. You got your green board, as you say, and instead of seeing a green board filled with big capacitors and resistors and very blocky type components, and you look at your anyone's ever been unfortunate enough to like drop their cell phone and see the inside of it. It is this compact little board with all of these different chips and connection points and everything integrated into it. And so, you've got all this high level, digital logic stuff talking, but at the same time, every time you got one chip, everything inside of it has been designed, and optimized to do that, but it still needs to talk to the other components. You still need to feed it power. You still need to make sure that, well, there's not something right here that's speaking really loud and is speaking so loud it's conflicting with what this chip right next to it is doing, because he's in his room and he's trying to speak to something else, and it's like having a really loud guy in your apartment, and the communication lines could get noise, and you got to deal with all of this. So you're working with the firmware engineer to make sure that, because they're dealing with the logic that's going on inside of all of these really advanced chipsets. And then you're dealing with, okay, how do I schematically connect everything? Like, what connection points need to go where? What kind of power do I need to put on this stuff? Where do I need filtering? And, all of this other stuff to make it. And then you also not just need to consider on the schematic level, but then you need to go to this whole other level of, okay, how do I actually physically put this together all on one board? And it's like a really big, complicated Tetris machine, Tetris game, where you're fitting all this stuff together. And then there's all these other rules where like, oh, this, not only do you have to fit it all together, but if this piece goes right here, all of a sudden it causes a problem with that piece. And there's, and essentially, so it's all of this fundamental electrical engineering kind of stuff that, was the exact same for when you're dealing with, just big old capacitors and resistors and op amps and other components. And essentially it's the fundamentals are all the same, but now you're still dealing with those to some extent, but now you're also dealing with all these highly advanced chips, and the communication back and forth to get it all to work.
Yeah, it's so interesting. It's like there's so much that's evolved both in software and in hardware, but some of the enduring principles about how you do engineering have really been pretty consistent over the past few decades. Olivia, tell me a little bit about how we go about designing electronics. I think maybe we could start with here's a startup idea, and if anybody does this, I guess you can pay us a royalty. But just let's pick like some IoT device, like a hacker hobby project, like let's say something to open a garage door from an app on your phone. So let's say we wanted to do that. That was the three of us are going to design this IoT garage door opener. How would you, as an engineer, start thinking about the design process for that device?
Yeah. So if you gave me that task of open a garage door from an app, the first thing that you sort of do is start to break it down into what little pieces do you need to do that. So, coming from robotics, a lot of how I think of things is in terms of, the brains, the sensors, and the actuators. So to some degree, when you do that, you're going to need, I'm going to need something to sense that somebody clicked this on their phone. I'm going to need something to actuate the opening of the garage door. And I'm going to need some brain that can link those together. So using, for example, a microcontroller, I might have as that sensor, a Wi-Fi chip that or Bluetooth, or however the phone's communicating with it, that, you program to send a specific, sort of logic when it gets the input from the phone. And you hook that up to the brain, and you tell the brain, the microcontroller, to, as it gets that, send something off to the motor to tell it, hey, start opening the door. And in between all of that, each of those little packages is going to have a set of requirements of other things that it requires in the circuit in order to make it work. So you have to do the whole power setup for it. Motors will take a lot of power. Okay, you might add a couple of extra chips there in order to make sure that it doesn't take too much and all of a sudden the controller and the Bluetooth can't work anymore. Then you might say, oh, this Bluetooth module needs, these specific other logic inputs to it to make it respond the way you want. And then you draw out those traces on your schematic. And then once you've got this sort of higher level thing of what you need and what all of those things need, and sort of that whole branching tree effect, then you can start working on the schematic with someone. And then that's when you turn it into a layout, which is then what gets put on your nice little green board, and you put it together and you start testing it.
Awesome. Yeah. So we started with kind of functional requirements. So your brain immediately went to, okay, you told me what the user wants to do. What are all of the different groups of functionality that we're going to need for this project? And I like this way you broke it out of saying sensors, actuators, and the brain, right? And then you immediately started thinking about, okay, well, how do those parts interact with each other, right? Phil, something you spend a lot of time doing is sourcing parts. So, we were talking about some motors and some different kinds of integrated circuits for detecting signals, and for the brain is probably going to be something like a microcontroller. So you've got the actuators for being able to move the door. Maybe you have sensors for tripping, whether there's something obstructing the door, that sort of thing. Tell me a little bit about, now that we have the functional requirements, the kinds of idea of what the components are supposed to do, how do you go about actually picking the parts that are going to go into our design?
So this is sort of I like the way you all laid this out, because I'd be you give this task to your Olivia and me, okay, build something so I can use my phone to do this, and I'd sit down with Olivia at the beginning of the project, and she'd be like, okay, I need to connect through Wi-Fi. She has these block elements, and then I'm like, okay, so you want to connect through Wi-Fi. What type of Wi-Fi system are you using? And then I start looking at different Wi-Fi chipsets. What are the community, what type of Wi-Fi bands do these chipsets support? How much space do they take? How big of this, are we making this really, really small, or do we have more space? Am I power limited? Do I need a Wi-Fi chip that, I can feed it all the power it needs and I don't care if it's efficient or not? Or is this operating on a battery? And I need to be worried about, okay, how much, I can't go burning through that, or, you're going to set it up and it'll work great. And the next day you come over and you're clicking and you're going, why isn't it working? Well, battery's dead, because you didn't have an efficient setup. So, these are all the kind of things where I'm looking at this, and you're constantly sort of, going through and looking at all these manufacturers, the different chipsets, and they're competing. You're seeing, okay, who is, on one side, there's, sometimes the newest thing can be a little bit problematic, because I know Olivia's, something comes out looking great, and, it could still be a little bit buggy because it's so new on the firmware side. So sometimes, depending on what you're doing, you take a step back and like, what is, is there something that there's been a lot of, testing on that makes it easier, on the software side? Or, is this something where we want to try and get the absolute newest, best thing on the market? And then is there something, usually you can't get the most powerful, most power efficient, smallest package altogether. There's usually some sort of trade-off. And so you need to take a look at what your larger design is and sort of optimize for that. And then, once you started selecting your components, like, okay, I don't need a full computer system, a laptop level processor to run this little thing. So I can, instead of going with like, a full processor, or even like a 32-bit, large scale microcontroller, I'd get away with, something like maybe just an 8-bit controller. Use something that's smart, but like, it just needs to be able to be programmed to do this one task. So you select that based on these parameters. You select your Wi-Fi chip. I'm looking at the motor thing, like how much force does this motor need to be able to output on this, and this is where you're going from that digital side back more towards the old analog stuff. You're dealing with, big motor systems and a heavy power system that needs to be able to feed that kind of motor. And as Olivia mentioned before, now you're, if you're also feeding a big motor on there, you need to be able to separate your power systems, make sure that, when that motor clicks on, that you don't draw so much power, you brown out your computer. So you usually, you now have a power management block. And you need to make sure that, all of this stuff is selected right in consideration of what you're trying to build, what your priorities are on, on this, size factor for us, how much processing power do we need to be able to put in this? What are the Wi-Fi capabilities? What are my power options? So all this goes into these design considerations for it, and you sort of optimize your chipset selections based on that, your different component layouts, and you're starting to basically take these functional blocks and say, okay, this functional block for the Wi-Fi unit, now here are our Wi-Fi options, and we select this one, and then we start actually connecting it to the rest of the system and looking at, now we're down into, instead of just, we've sort of selected the component we want to use, and we're starting to actually get into the deep part on the hardware side of, okay, how do I physically set this up? What are the main connections? And then how do I lay this out on a board? And then, usually, sometimes I think the next question would be, well, after you have this design, then, the sort of building and testing process. And so, do we want to, rather than jumping straight to sort of just design it and try and push it out, usually, you're grabbing all these components in your lab and you're wiring it together. And then I go over to Olivia and like, okay, these are sort of the functional groups. We've selected these chipsets out. We've Frankenstein some development boards and evaluation modules and other stuff, or slapped it on, a quick board that, we printed out either in-house or quickly sourced, and we sort of rig up this prototype design of what we think we're kind of want to do, and take it over to your firmware parts. We're like, let's start seeing if we can get this thing working. And so it's that whole process.
So that's great, Phil. So you have an idea of how you're going to source all of these different components, because there are different kinds of microcontrollers, different kinds of actuators and power units. And you're considering things like, well, what is the operating condition for this device? And then you're looking at data sheets, right? The kind of advertised functionality and features for each of these components. You're balancing those against availability. Like, is this an obsolete part, or is this something that I can buy very easily? As well as cost, right? Because cost is always a concern. With some components can get pretty expensive, and others are, cost pennies for thousands of them. And so, you're considering all of these things. You source these parts, and then you mentioned something called a dev board. Olivia, can you tell me a little bit about at this part in the design where we've got some sort of candidate parts that we're going to put into our overall solution? We're either going to develop or we're going to buy these dev boards and stitch them together. Tell me what those are and why we do this part of the process.
Yeah, so dev board or development board is sort of your debugging best friend, both for the software and for the hardware of it. And often you can use an off-the-shelf development board for some parts, which has their nice little compact IC on it, and then it breaks out to all of these bigger pins that are easy to put your multimeter in or hook something else up to. Or you could do it in-house with breadboards. You take, maybe a bigger version of the thing that you're going to use. So, for example, if I'm using a specific microcontroller, it's probably going to come in, 3 different sizes that are attached to things in 3 different ways. And I take the big one that could plug into this big chunky breadboard, and I put a bunch of wires in it, and then I can start testing the firmware on it. And if something doesn't work, then it's very easy to take a probe and poke it in there and say, hey, is this being powered properly? Is the problem that, this signal is getting, there's the noise problem with your roommate screaming at you while you're trying to whisper on the phone. Is it, are things moving too fast, too slow? Is it the software that's the problem and I see that nothing is moving when I think it's supposed to be? So dev boards are sort of this nice intermediate step that can really, really help the debugging process and sort of let you parallelize the work that you're doing. As once a dev board is hooked up, Phil can go and start making his miniaturized or most cost-efficient or whatever optimization parameters we've chosen version of like a final board. And I can sit there and start tinkering and make sure that my digital logic is working the way that I think it should, and that it can, communicate to a larger software application the way that I think it should be able to, and that sort of thing.
Right. And, sometimes we find out, oh my gosh, yeah, actually we sourced this part and we don't think it's going to work for our application. And it's a relatively straightforward process for you to go and get a new dev board for that new component, bring it into your design and do development and testing on that. Right. And there's parallels to this for software folks where, we'll sort of build what we call like a minimum viable product or something that, does the functionality that we need and no more. And maybe there are some parts of it that aren't optimal, right? Like there's certain speed ups that we could have, or we could parallelize something. But what we want to do is just make sure that end to end, it does what it's supposed to do. And we can do some sort of basic functional testing. sometimes there's an intermediate step, right? Where Phil, I've seen you put these together, but proto boards. So tell me a little bit about what a proto board is and what kind of that represents in this process of designing electronics.
So depending on, a lot of the times we're using these dev boards. They're, company makes this microcontroller and they want to make it very easy for you to develop something on it. So they sort of pre-make that. And my kind of general rule is, well, if they don't have a dev board for something, you can make one. It can be something as what Olivia mentioned earlier. You can simply take a breadboard, which is this kind of big plastic thing, and it's where you can like stick actual wires into it. You can plug the things in just like almost with your battleship. Stick your big processors, your big carrier ship over here, and then you've got your little logic units, which are your other little ships, and you stick them in there, and you're sticking wires to connect them all. But then you've got these different proto boards. There's different levels of. So the breadboard is kind of the simplest, easiest way. It doesn't always work for some components. There's the proto boards, which there's kind of an entire different field of those now. So you can get in the old school kind of what you'd see is you get a sort of a copper sheet board and have pre-drilled holes, and you could slot things in there and start soldering stuff together. A lot of the times, when I think of a proto board now, like we have a machine over here where instead of if I've got a design and I want to sort of test it out, but I don't want to spend either the money to go get it fabricated professionally, or there's, I need to do it quick and I can't spend, even I can't wait for, a week or two to get this board back, or I don't want to pay the really high cost of getting it done, really quickly. We've got this like 3D printer machine, which actually uses a sort of silver-based epoxy compound, and literally you can print out traces, and so I can create, just really, quickly sketch up a design and print out this sort of custom board, for prototyping this unit on. And so, basically it's this combination of all this stuff, and the whole goal here is to basically, there's always the difference between how something looks schematically and then how something will actually work in reality. And you need to be able to do these checks. And instead of, doing a long cycle where you try and build the schematic and then you do a big test run and then you have to go back and solve it and redo that process, you're sort of testing it all. You're testing these out at a component level as you're adding stuff, or, if you got two things that look like they might both be options. You could grab, a development board or a proto board, your own option for this, test them both out. And, then maybe once you have a larger idea, take a couple of the components and put them all onto, this quickly fabricated board that you can breadboard together, or we can make a little custom board. But it's all about letting us testing it, because if you're testing it as you're designing it sort of stage by stage, it's a lot easier to debug. And it's always kind of interesting to debug, between, is it a hardware issue or is it the firmware issue? Because they're so interlinked now.
Right.
As Olivia was saying, when she can stick things in there and something's going wrong, and I can grab my, it's like, oh, these two chips aren't talking to each other. Why? And, I grab my oscilloscope and I run over and I plug it in there, and, plug the oscilloscope. They've got these awesome new ones. You run it on your computer, and I can monitor all the stuff, and I can be looking out there and like, okay, I see, like, I can see literally the digital logic flowing over here, and I can be like, oh, wait a minute, that's not at the right voltage level, or there's some other issue on it. I see a bunch of noise, or I'm going, wait a minute, I'm seeing, this looks like what I think the logic stuff that should be going across it. Let's go back and check if there's something screwy, if you've got a little gremlin running around inside of your IC that's in the firmware land. So, it really helps to be able to test these at this different component level and be able to split it up.
It's easier to debug issues when you're at the dev board level, right? Because it's so easy for you to get your fingers in there and check all the connections and swap components out if you think something might be broken. So you want to solve problems as you go along incrementally, rather than sort of spend a whole bunch of time putting a board together, getting the board as a finished product, and then finding a whole bunch of problems in it that you've got to you've got to debug once everything's all congealed together, right?
The really nice thing is, we have all this technology now that makes us really cost effective. As you're talking about, you've got these off the shelf dev boards. You have a dev board, it used to be, well, you either grab your breadboard or your old proto boards with holes, and you're sitting there trying to solder stuff together. And there's all this technology now that makes it so much easier and quicker and faster and more cost effective. So we can, we've got a lot of versatility in being able to do this without needing to rely on, very long professional fabrication runs. And even if you're not doing something, let's say you're doing something that doesn't require the space requirements of really fine tolerance of really costly manufacturing stuff, that like the stuff in your cell phone, it's really crammed in there, and you need some really high level fabrication tolerances to do it. But if you're not dealing with that, there's also, essentially what is kind of, I know the makers, the whole DIY and maker community are really happy, because now, they can stuff that doesn't require quite that level of tolerance and miniaturization, you can get pretty cost effectively. And at the same time, now there's also all this other equipment out there that you can get where you sometimes don't even need to go through that process. You can simply, do it right in your lab. Sometimes you need, you don't necessarily need even a really, really expensive, high level lab to do some of that.
Yeah. And the maker stuff is so interesting because it really lowers the bar for people that want to get involved in something that up until pretty recently was very capital intensive. You couldn't sort of mess around with hardware development in the same way that you can software, right? If you've got an internet connection and a laptop, you can get involved with software engineering. Whereas, there's obviously a physical component to a lot of electronic design. So it's an exciting time. Kind of along those lines, Olivia, you specialize in programming these teeny tiny computers, which are very interesting and unique in their own right. Tell me a little bit about what that looks like. So say we have this dev board set up. You've got a microcontroller. You've broken out a bunch of pins. They're connected to the different subcomponents. If it's a garage door opener, maybe we have, the motor control. We've got a sensor for the door being blocked. We've got some maybe Wi-Fi chip that's handling communications. Now it's your job to program the firmware for that microcontroller. Tell me a little bit about, pick a family of microcontrollers and tell me a little bit about what that setup would look like.
Yeah. So the family that I've done the most work with are AVR 8-bit microcontrollers. And a lot of times when you go and you're choosing what controller you want, you'll also look at the documentation for it, sort of the hardware version of, your Doxygen or something. And you go through it, and they hopefully will have, a thing on the easiest way for you to program these things. Because unlike running an application on your computer, I can't just compile my C program and then, make my executable and run it. That doesn't work. So there's oftentimes this intermediate bit of hardware that you use to sort of translate whatever your original program is in whatever language you wrote it in, probably C, and then turn it into the type of executable that the microcontroller expects. For the 8-bit AVRs, they expect an ELF program, and then they change that into an Intel hex executable. And then you feed it to these intermediary devices, which then they'll reset the microcontrollers to a mode to accept a new program, and they'll handle all of that initialization so that you can go and you flash the program into the microcontroller's flash memory. And then it translates this file into exactly the stream of bytes that'll be permanently recorded on that controller until you next change it. And then you start it up, and it'll reboot it usually at the end of its process. So you can immediately see, hey, has this code that now has gone through 3 different steps to be compiled to the right type of executable and then put onto this memory? Does it work? Is my light blinking? Is my motor moving? Can I use my Wi-Fi?
Right. And it's so interesting because these chips, most of them don't have operating systems, right? So you're like, in some sense, writing an operating system for this chip. It's the only thing that's running on the processing unit. And while that environment can seem a little daunting to a newcomer, I think there are a couple of tools that are really helpful. Number one is, there are ways of debugging these programs, right? Yes, you have JTAG, you have also serial debugging, so you can make print statements inside of your program and then observe different values coming off of the microcontroller. There's blinky lights and things like that. And there's actually, so AVR is a really neat family of microcontrollers because, the original Arduinos are the 328P is an AVR microcontroller, if I'm not mistaken.
Yes. This is one of the things where I really love the maker community because they make all of this even more accessible. Even if you are someone who's done it for a while, oftentimes, there will be an upgrade or you'll switch to a slightly different variant of it. And you could spend your months and months seeing every little difference from the thing that or you could go and somebody in the maker community has probably written up a quick guide on, hey, if you're used to using, this teensy 2 and now you're using a teensy 3 and it's got this different microcontroller at its heart, here's the fundamental things that you can start looking into on why they're different. And here's a couple of easy ways of debugging it, here's some pitfalls to watch out for. And it's really nice to have that sort of starting block to look at rather than having to do all of that legwork.
Right.
It's sort of I like to think of it as like the hardware version of the Linux community.
Totally. Yeah, that makes a lot of sense. You put more devices in the hands of more people. People are going to get passionate about building tools and applications and sample projects around those platforms. And then you get this kind of virtuous cycle of people contributing and helping each other online, and it generally improves community and knowledge around that thing, so that it becomes easier and easier for you to develop on the platform. Which, of course, is like the dream for the chip maker, right? Which is why I think we've seen so much embracing of the maker community by the industry. So, Phil, as Olivia is doing all of this work, developing the firmware to make the system do what we want it to do, she mentioned that we can now parallelize a task of taking these components and thinking about how do we make this production ready. So we're going to take all of these different integrated circuits and connections and resistors and capacitors and power supplies and these sorts of things, and we're going to bring it together into a printed circuit board. So tell me a little bit about how do you design a printed circuit board before it goes out for fabrication?
Yeah, so one of the nice parts, as we said, we've got these development boards, evaluation boards, the whole breadboard, proto boarding, and the rest of that. And I wouldn't even say it's not so much that you're paralleling your process, because there's actually this constant back and forth between the hardware and the firmware side. We're like, okay, let's try this chipset, and you put it in there, and we wire this board up in one manner, and we're testing okay, this firmware is working. We add this component, and all of a sudden things are not working, and you're like, okay, there's a hardware issue here, and you swap that, and sometimes it's software, and so there's this. What it does allow is, instead of having to build the hardware, then build the software, and then test it, the software and the hardware are sort of being built and tested at the same time. So, got Olivia over there, writing the code for these different microcontrollers and integrating with them the components pretty much at the same time as I'm adding more stuff to this design and fleshing out. But then you get to a point usually where, okay, we've got a setup now that we're pretty happy with, and we think this is going to do our goal. And now we need to take that sort of, we've taken these block elements and we've fitted them out with the components, and we have our schematic design of, okay, this is how these different chips connect. And now what we need to do is we need to lay it out, because we need to take all of that, and instead of having a big, it looks kind of like a wire spaghetti mess sometimes between different boards here and there and breadboards and other components. You got wires going everywhere, and it sort of works, but it's not something that you want to stick in your garage to run your garage door open. You want something that's in a nice little box or something.
Well, you may also want to make 1,000 of them. Right.
Yeah. Or for a production run. So, you got to take it from that you've tested your schematic design, and now you need to actually figure out how you want to build it. And so, there's usually at the beginning you're like, okay, I want to fit this, into some particular form factor, and you're sort of running on that. And depending on how small you want it to get and what environmental factors you want to deal with it, because if I'm building a car door opener in the main United States, it's going to be along one lines. But if I'm like up way in Alaska. And I mean, like, somewhere, where this thing might like be way down at frozen temperatures. There's a whole set of like other physical aspects for those a harsher environment that I need to design for. But you take all of that into consideration, and you sort of build out, there's a design set rules like, okay, we need these particular types of tolerances for environmental, and because we're making it this small, we can use these particular fabrication techniques. And with the miniaturization that we do nowadays, there's a whole slew of really cool new advanced things. Everything from doing things like, instead of just we have all these really really small components. There's a lot of BGA type and micro BGA components on here.
What's a
rather than
BGA?
just your standard label. A ball grid array. So if you've ever seen a CPU, and at the bottom, it looks like there's just this matrix grid of all these looks like little dots. And essentially, instead of having an old school chip where you see it has these like little legs coming out off over the side, instead they've got all these outputs on the bottom, and they literally have little balls of solder. And so when they put it on the board, and they usually use a reflow technique for this, and essentially the solder, sort of this little ball of solder melts and connects to the pad underneath it.
It's because there's so many connection points to the IC that you can't actually physically make that many legs on the chip, right?
Yeah, then there are like micro leg designs where they're really small legs and all packed in there. But even still, the modern, you get chips with, over 1,000 connection points on a single chip. That's like, just a couple square, millimeters, on a couple millimeters on a side, and it's just packed with these connection points. So, in the miniaturization, they're always figuring, okay, how can we, take all this really complex stuff and just squeeze it down a little bit more? And there's all these different levels. So, there's these different type of components going from your standard, you had in the old school, the dip switch or dip connection kind of, would be what you put in the breadboard. And then you got your T-SOP, and there's a whole field of different types of the leg connectors, and basically going smaller and smaller. And then you get into BGA and micro BGA, and there's a couple different ones, and essentially just all about how they're repackaging it to fit in a smaller form factor. And then the smaller you go, you need to start considering different fabrication techniques, because you need to route all these. Sometimes you're just dealing with like tens of channels, and then you're going to hundreds or thousands of connections running through this board, and you get into how many layers do we need? Because sometimes you build up this on a simple board, you got maybe just it all on the top, or maybe you have a top layer and a bottom layer. And then you can start stacking layers, and you can do things like I'm going to have a ground plane here to actually help, cancel out noise from these lines down here, from these lines up here. And you get into all this really cool stuff about how do the electrical properties, get affected when you start talking about not just sort of a schematic world, like this device is connected to this device, but this device is now connected with this type of material around it, with this length and in this setup. So it's sort of the physical world factors that go into it. And so you take all these parameters and build that, into your design. You can do everything from a fairly, simple setup to some truly advanced ones. And the really advanced ones, they're now doing things also like, instead of the capacitors on the top, sometimes they'll have, like inbuilt capacitors into the PCB, where they've got capacitance film, in this layering mechanism. So instead of these individual components, you've got these really super advanced boards where they're literally, before they were just smashing the stuff into the chipsets. Well, now not only do we have these advanced chipsets, but you're getting these advanced boards where you're sort of consolidating, even more components into just the board fabrication.
Yeah. So, and it's such an exciting area of technology, like how PCBs work. So, I mean, there are two, just zooming out for people that are not really familiar. They look at these things, it's like, all right, well, there's this green board and they're connecting a bunch of chips together. There are really two fundamental roles for a printed circuit board, right? One is the electrical connections between all of the chips. So that's something, Olivia was talking about, where we would have these dev boards, these development boards, and then wire things together so that they're connected in a certain way. So the PCB, the printed circuit board, will handle those connections. And the second thing is actually physical structural stability. So it holds the chips in place and gives them a rigid structure, so that they're not, unlike the spaghetti wires that we see when we start building these dev environment setups, you're not like knocking wires loose and things, right? So, Phil, you were talking about how these different layers, these different planes on the PCB serve the function of connecting the integrated circuits in a certain way that we've already figured out how to do in the dev setup. But you're actually having to physically design those connections. So tell me a little bit about the programs, the CADs that are available to design those connections, and what does that process look like as you're going from the dev environment into a finished PCB design?
Yeah, and so you have these computer aided design programs that can do practically anything. And there's an entire subfield specifically for um, not just electrical engineering, but sort of the hardware design, and even within that subset, there's quite a few different ones. So I'm if you're more on the electrical side, and you can use this these computer systems to essentially lay out, okay, I think I have these chips and these components, and put it on there, and with like a SPICE program, the computer can actually calculate and simulate what you're doing, so you can sort of try and test out some of your circuitry without even needing to do, to have an idea of what it's going to be like before you even, start putting the components together. And then you can take that. And so with the, so you can actually, you've got that whole category to actually test out your schematic design as you're laying it out. Because the first step is if you heard me saying schematic. So what you're doing at that point is you're not even considering the physical aspects. You're looking at, sort of take your block group, or you say you had a Wi-Fi chip at this block area. And now we've selected the chip. And I know with this chip, I've got, let's just say, like 32 connections on it. And in the schematic, you've got essentially a block, this is your chip, and it's got all the connection inputs outs on in there. And you lay it down, and you're saying, okay, where are all these 32 connections going to? These ones are going to power. These ones are going to ground. These are for communication. These ones have some alternate function that we're not using. You figure all that out, and you sort of lay it out in sort of like a sort of wire block diagram of how everything is connecting together. And
you're
that's
turning
your
the spaghetti from the dev environment into spaghetti on the computer screen.
Yeah, exactly. And the nice part, so I was talking about, SPICE programs before, where essentially you can take that and it can actually start running calculations and simulations on it. And then you can take that schematic, though, when you're ready to actually go to the sort of the production phase, and there's different versions, but essentially what you're doing is you're taking those schematic files, and they'll have what are called footprint files that go with it. So that Wi-Fi chip with the 32 connections, well, in the schematic, it's just a block with connections like 1 through 32, and the footprint file is, okay, here's the physical dimensions of this chip. Here's where the actual pads are. And there's an association between that half of the program where you take the schematic design. It actually creates what's called a net listing, or sometimes referred to as like a rat's nest file, where essentially it's looking at all those nodal connections between, okay, here's all the power connections on this power plane. Here's where these signal lines are connecting these different components. And it takes it over to this PCB layout side of the software. And you've got these footprint files that tell the computer, okay, here's the actual physical layout of the chip. Here's where the actual connection points to those chips are physically, the sizes, the dimensions, where they're laid out. And then it associates all of that data that you did on the schematic one to the actual pins in that footprint file. And then you're there starting to deal with the more physical side of the thing, where
this is the
how
Tetris.
close can I put stuff. Yeah, this is it's a big complex Tetris game with a whole bunch of other rules, where you can't put two green blocks next to each other because they'll do bad things, and you want to try and sort of fit everything together in a nice, neat, a pattern where it's everything is sort of working in as small of a space as you can get it. And everything's working efficiently, and nobody's juggling each other's elbows. And it's kind of, if you're, kind of like if you're, the old big clock makers, and you're looking at a watch, and they've got all these different gears sort of spinning together, and they're like, how do they get all of that stuff to work in synchronicity with each other in such a compact design? And it's like that, except instead of mechanical gears, we're dealing with, all these different chips and electrical signals, and you're fitting into here. But essentially the program, you're able to sketch it out, with the schematic one in that program, simulate it sometimes, and you take it over here and you start dealing with this layout. And then there's also a whole bunch of simulation programs you can add on to that side where, let's say if we want you can take it and take like do a sort of a rendering of it to see like, hey, this is what the layout would actually look like, with you can import STL files, step files for what the actual chips would look like, not just with their footprint of how they attach to that green board, but physically in the 3-dimensional aspects. And then you can also do things, you can do more advanced analysis. Like if you're worried about, okay, how much power are we pumping into this small board? And I want to run, a thermal analysis. And there's software that will take that, and you can, it knows, okay, it has all this information about how this chip is operating and the power parameters, how the power is going to dissipate. And now it also in this layout format, and it now knows the 3-dimensional positioning of all this stuff. And the material, you can tell the parameters of the material you're using as that when you look at that green board, usually it's like a fiberglass based board. There's different types for electrical reasons and sometimes structural reasons and thermal reasons and all sorts of different stuff. But it can take you, if you know all that stuff, and they have these big computer programs that they've had some computer wizard go through and program, and you can run these really deep simulations and analysis on the board for a number of different things. For thermal, we talked a lot of time about all these noise issues, with really high speed connections pushed into a really, really tight, compact area. You got to worry, it's like having a whole crowd of people all stuffed into one room, and you need to make sure that everyone, you've got a half dozen different conversations in here, and that nobody's conversation is interfering with somebody else's conversation. And
you need to soundproof the walls.
Yeah, well, sometimes you can have the two people are quiet enough where they can be right next to each other and they're talking fine and can hear each other fine. And so you got some really loud guy in there, and you're like, okay, stick a little, a little sound barrier between him and the other guys, so he's not over talking everybody else. But there's for that analogy, there's there's these analysis programs you can run in this layout where you position and you can do this really deep analysis to sort of predict where you're doing, because half the time you're doing like, okay, I understand the electrical properties of here and I have a good idea of how much noise this component might be able to do, but without sitting down there and running through the calculations by hand, you don't know for certain. So after you've been doing it for a while, you sort of you have a good sort of understanding, because sometimes you had to actually sit down and run the calculations by hand, and other times you've worked with these components and you know that, okay, this type of system is going to cause this much interference and I can generally get about this close. Yeah. And sometimes it's it's good enough where you're like, okay, I know this isn't going to do it and I can push it right there. And then other times you're like, okay, this is close enough or complex enough where I need to actually do some additional analysis, and unless it's a really simple circuit or a simple setup, those calculations, it gets to the point where you can't do it by hand anymore, or at least you shouldn't be, because you're going to be spending a long time doing it. And there are these programs that are integrated into this design software, this CAD software, to do all of this. And so you've got this whole really nice, the computer aided design. I think the main programs, there's Altium, there's AutoCAD has their Eagle software. KiCad has come a long way. Particularly, I think CERN started funding their development. They're kind of the open source one, and their software, they used to lag behind in some of these really expensive professional setups, but they've made a lot of advancements. They've got a very nice software suite now too. I think OrCAD, Cadence, and you've got all these different options. There's a good bit out there for different ways to do it.
To take a bit of a step back from what he's saying, going from that schematic to that physical layout with the rat's nest, as it's somewhat affectionately called, it makes me think of those little puzzle games you might play on your phone or your computer, where you have a bunch of circles and a bunch of things between them, and you have to drag the circles around so that nothing's crossing, except it's wires instead of circles that are being drawn onto a board. And sometimes it's impossible. And that's when you have to figure out, sort of the bridges, which is adding another layer. And then it's, how do I make sure that the bridges aren't overlapping?
Three-dimensional chess.
It's that point where I always think of it as cheating, where you're like, okay, well, this design doesn't work. Let me add in some of these, a couple more layers, or some other advanced fabrication technique where I get the cheat and like, okay, that doesn't work well. We add in this little additional layer or setup to
but
it.
it
And we can
increases costs and complexity.
yeah, but it's one of those things where if you want to design something truly small, like I mean, if everyone has the AirPods now, and if you think about it, that thing has there's a Bluetooth component and there's a power component, there's the speaker, there's all this stuff, and it's crammed into such a tiny spot, and the amount of thought, they've got some really advanced stuff, custom type ICs that they're developing specifically for those purposes, which is beyond what unless you're a very high level big company that can afford to do that kind of stuff, you're not going to get quite to that level. But even in just like the maker community, if you optimize everything well, and set it up well, you can really compact down, even to what would have before, even like 5 years ago, been considered something that you need to have
Right.
a lot of funding behind to be able to do. It can be
For
done
sure.
a lot cheaper now.
Yeah. So you have this, like Olivia was saying, you go from a schematic where you're making sure that you are connecting all of these things at a logical level where they need to be connected, and then the board layout is where the rubber meets the road, and you've got to figure out physically in this physical universe, how do you get those logical connections to happen in a way where all of the thermal characteristics and the EM interference is at a level where the thing still works the way it's supposed to. In addition to working in the form factor and under the constraints, the operating constraints, like if it's going to go in somebody's ear versus something that can sit in a project box, they're very different ideas. So let's say we have a PCB layout from in KiCad or in whatever software we're using that we're really happy with. What do we do from there?
At that point, you've got all these different manufacturers, and depending on, usually you're dealing with, just either a 2-layer board would be the normal type, or sometimes a 4-layer if it's a little bit more advanced. But you take a look at, basically how small are these little traces you're designing, and the vias, basically the holes that go through to connect the different layer points. So when, as Olivia was saying, you do the little game and you get stuck because there's just no way to uncross it, these lines, and then I come in and I cheat and I add a different layer, and so basically I've got something that'll pop from one layer, go underneath, and pop back up, and you've designed all this, and basically you need to take a look at, well, usually as you're designing, you've sort of pre-picked out, what tolerances you want to meet. Okay, I can only use traces this small or vias this small. This is generally the design constraints I'm designing that around. And then you go to your manufacturers, and you've got there are a lot of manufacturers that are actually tailoring themselves to sort of the more maker market kind of design. So if things don't need really really fine, super accurate tolerances on things, you can get them for quite cheaply compared to at least what it used to be. Where it might have been a really big deal to get something made before, and I can pay like $50, and in a week and a half have a board back that would have cost me like $1,000 a couple years before. And then with the more advanced stuff, you've got a whole slew of these advanced fabrications that can do all these advanced processes, these multi-layer boards. Sometimes they're literally embedding components inside of these layers, or they're using super thin layers. So, you can have, we were talking, 2, 4 layers. Well, you can get like, 8, 16 layers, all crammed into this board, and they can do it at sometimes like half the thickness of a normal one, or using some sort of special material, or all sorts of different options for this. Instead of using a drill to drill out those vias, they can use a laser to have to create these micro vias, all these advanced things that they can do, and that's how
Yeah.
you get into the really really small miniaturized things. But essentially you sort of pick it out, and you send it out to the fabricator. And then there's also, that's just to making the board, that little green board most people think of when they think of it. But then you also got to think about, okay, now how do I get actually, I've got this board, I've got all my components selected, but how do I get the components on the board? And a lot of the times you'll get your board and you're just doing that by hand. You've got your solder station or your rework station, and you're putting it on there and you're soldering it. and just attaching it by hand. But then sometimes there's either the complexity, or you want to streamline it, or it's just a really really small component, and so doing it by hand is really difficult. And so they have these what they call an assembly house, or sometimes you'll hear of what is a turnkey assembly, where they're doing both. Basically, you give them the design, you say, okay, here's the list of the components that I want to put on it. Yeah, they call it the bomb. So a lot of times we're talking about, where'd that bomb go? Did you have the bomb ready? And you get somebody else in the office looking down, and you're like, what are they talking about? But yeah, so you got this bill of materials for all the components, where you're sourcing them from, and those you're talking about the computer aided designs. Well, not only can you design all this, but then you can output different file formats for, okay, here's how the structural layers work, and then here's the different positions and orientations of all these different pieces, because it has all this information about the physical properties of it. And you can take all this stuff, output it, and give it to these assembly houses or a full turnkey fabricator. And they'll take it and they'll produce the board, and then they've got some, usually what's called like a pick and place machine is a popular one now, where if you've ever seen the videos on there, and basically it's this machine, it's got the board and it's got this little arm that's zipping around like a suction cup, and it's picking things up and spinning them around and putting on the board, and it's amazing to watch it just how fast this goes. But essentially they take all that information, put it into the machine code format that thing sets it up, and then they just feed the components into it, and it literally takes all that stuff and sets it up on the board. And then they do what's called usually for that would be a reflow process, where instead of hand soldering something, what they do is they put on solder paste, which is essentially the solder, but instead of having it in a solder wire, it looks almost like an ink or a glue. And essentially what it is really, really small balls of solder suspended in a sort of a flux type gel kind of material. And so they layer on just enough of that's been calculated based on the design and the computer, these different CAD tools you're using to help design it. And you lay all that out and calculate, and it places the right amount, and then it places the component on it, and then they basically shove it in an oven. And there's these different thermal branches. So usually what they do is they'll heat the whole board up to a temperature right below the solder, what melts the solder, and then they spike it up there just long enough to melt the solder, let everything attach. And it's really cool to watch a video of this happening, because what actually
it's almost like a potbelly sandwich, right? Like going through the
oh yeah, quite literally. But then the coolest part is, not only are you watching the cheese melt all over your sandwich, but the surface cohesion. This is where you're getting really into the physical side of things. For a reflow process, the component might not be quite positioned just right. It'll be on the pads, but not quite center. But then because it's got this even number of pads, and when the solder melts for just that moment there, the surface cohesion, that little solder will literally straighten out the chip on the board, so that there's even tension between all those melt points. Then that's a very popular manufacturing technique nowadays for large scale production. Sometimes there's different types ways to manufacture it. So usually the pick and place and combined with a reflow technique is very common and popular. There's tons of awesome, really cool machinery that does all this. A lot of the times, if you're doing large scale productions on sometimes not as miniaturized components, they'll do what's called a reflow machine, not a reflow, a wave solder machine, which is, you'll see what looks like think of the car factory. You get those little assembly tracks, and you see all the stuff rolling around there. And they literally will have like a molten solder waterfall, or sometimes a little pool of molten solder, and you'll see the stuff go through that or dip down into the solder thing and come out. And it's literally like, they're flowing this wave of molten solder over it. And letting that create all these connection points through the system. And different techniques, depending on how you're fabricating it, will sometimes involve different design considerations. And usually you'll decide pretty a little bit earlier on, like which one you're going to go with. But there's all these really cool fabrication techniques to do different things that you can then choose once you've sort of designed your circuit.
Yeah.
And then send it to them and get back, either your boards or your fully assembled boards, and you're ready to start testing and hopefully do a minimal amount of debugging.
Yeah. So, that's a great segue into kind of like the next step here. So you've got, you send these bombs out, the schematic and your board layout. let's say we use one of these turnkey assembly things and we just get finished product back to us. Olivia, now you've got a handful of boards. Tell me a little bit. That doesn't have our software on it. It's just sort of like the integrated circuits connected in the way that we wanted them to be connected. But we're still a bit of a ways from done. So tell me a little bit about, given these boards, what do you do?
Right. So you get your nice finished board, and as part of your design process, even as you're miniaturizing everything, you need to make sure that you leave yourself a way to program it, because otherwise you've got this really cool looking green board that does nothing. So if you're going for something with a brain, there are also pure analog things, but not quite what we're going for. So you still have to go figure out your way. With my example of the 8-bit microcontroller, it's got its little tool that it uses to program it, and now you've got to put a different end on it so that you can, attach it to what is probably a much smaller connection on your production board. And you go and you flash your software onto it, and then you watch it work. And a lot of boards will set up some sort of a debug port, which we touched on a bit earlier, be it JTAG or serial. And if it's your first couple of boards for a run, you might have, a version of your software with extra print statements or something. When you're first, deploying your application, you might have a debug mode that you can then turn off. And it's sort of the same thing. You do that and you watch it, and it's, you make sure that the logic levels are doing what you want, that it's communicating the way you think it should, with that extra debug information through that nice little port that you built in. And then when you don't need it anymore, you can put on the production software, and then you sort of, usually people will cap the port or take that chip off or have some way of making it not available unless you're selling it to someone else who really needs the debug port. And then,
which, by the way, in episode 5, talking with Rob Peasley and Brian McCord, is a step that often gets omitted, and is a wonderful gift to the reverse engineers taking your designed electronics and trying to subvert it or figure out vulnerabilities. So it's a really good point. And it is indicative that you work at a security company, that you thought of this step in developing your electronics.
Yeah, it's a hacker's dream and a production run's nightmare. Forgetting that step.
Right. So you develop, you put your software on, which you had developed earlier in the process while you were having the dev boards and sort of the spaghetti setup with the breadboards and everything. Mm-hmm. You put the software on there, but then you've got to go do some testing, right? So tell me a little bit about what testing looks like, even using some examples of what you do in your day job. Like, how do we develop test plans around things and make sure that the electronics do what we intended them to do?
Yeah, so the sort of two main batches of how I think of testing things is sort of a full functionality things and test, where you sort of probe where the edges of things are, because a lot of both hardware and software doesn't necessarily think of every single edge case of, what happens if it's expecting a number from 0 to 9 and you give it 100, or the hardware equivalent of, did you build in protections for things like, if this is expecting 5 volts, if I feed it 5.5, will it fry? Maybe what you're doing is so specific that is okay, but that's still something that you need to sort of stress test. And then the other sort of testing is what I would call, a volume test or a usage test, where you take, your garage door opener, and you sit there and you say, okay, what if I run this 100 times in a row? Will it, still work the way I think it does? Does it heat up too much? Sort of some of these problems that we were talking about with the physical electrical design. What happens then? And once you get both of those sets of tests done, you can sort of put together a plan of, okay, these are the circumstances in which everything works the way you think it should. These are where it starts to act a little bit, on the fritz or something. And, a lot of, it's sort of the software equivalent of a lot of electrical data sheets will have these curves of, ideal operating conditions with, temperature ranges and current ranges and all of these things. And it's sort of your equivalent of that, of what are your ideal operating conditions for this hardware, firmware, software interface. And, if things start to go awry, that testing will also usually give you some idea of how to get it back on track, how to recover from if something does go wrong, and all of that important and occasionally overlooked.
It sure is. Yeah. And by some really talented engineers sometimes. I mean, there was an article that came out 2 or 3 weeks ago about Tesla had its main processing unit failing because one of the flash memory chips was receiving Linux swap files and getting read writes over and over and over again. And one of the things about flash memory that you two are well aware of is you only get so many read writes out of it, and if you are kind of frivolously writing to this thing over and over and over again, if you give it 12, 18, 24 months, it'll just fail. And now you've got what they affectionately referred to as, a consumable item in this soldered on, flash chip that they've got to go replace in, who knows how many vehicles, right? But one of these examples of if you're not reading what the design constraints and intended usages of the components on your design are, it's going to be really hard to test those constraints.
Yeah.
Awesome. Well, Phil, you told me a little bit about some of the kind of up and coming things on the PCB side that you're really excited about, these kind of more complicated layerings and micro vias and embedding things like capacitors inside of traces rather than having to put them on the board. That's really exciting. Olivia, what are some of the things that you're excited about on like the firmware and microcontroller side that you see trends in the industry?
Yeah, one of the most exciting things is just seeing how much smarter all of these things are becoming over time. 5-10 years ago, your 8-bit microcontroller, yes, it's got its inputs and outputs, and that's what it's good at, but it might only have 3 or 4. It might only support this one specific serial thing and this one specific peripheral thing, and that's, you've got more flexibility than a circuit that does only one thing, but still not a lot. And as new things come out, you get to see not only are the packages getting smaller and smaller, but you get more and more flexibility in the firmware in terms of, okay, now I have these 4 different options to talk to all of the other chips, which means that now I can use different types of chips that might have been blocked off before because some can only talk over SPI versus I2C versus just some generic GPIO protocol, and sort of just giving you more flexibility, more access to parts that you couldn't use before. Another thing is you start getting more memory on these systems. You get more RAM, you get more flash memory, which means that the programs that you can write for these small controllers can now get larger and larger. Not necessarily I'm going to write the most inefficient program ever, but now things that might have required an entire CPU can be done on these tiny microcontrollers instead. So now that opens a whole new wave of embedded applications for things that would have required a full computer instead, 5-10 years ago.
Awesome. So we're getting more flexible and cheaper components, as well as more flexible and nuanced ways of sticking them together on the PCBs. So it's a pretty exciting place to be. I guess last question is for people that are interested in getting involved in more electronic design and maybe have a bit of a software background. Where can they start?
When I started getting into this sort of firmware type design, I read all of the maker books coming back to the maker community. There's Make AVR, all about those 8-bit microcontrollers. There's Make, electrical design part 1, 2, and 3 with different sub-focuses. There's one specifically for different protocols to talk to different types of chips and the intricacies there. And really, going between that and, the forums that you might see and just looking at what people have already done and trying to understand that and reading, that sort of background information, I think is a really good place to start.
Awesome. Phil, do you have any recommendations for people that want to get into a bit more of the hardware side of things?
She listed about half the ones I probably would have started on. I'd say the other thing for like me, there are all these awesome kits out, that are perfect for like, students that, are kind of have an interest in this, or even if you're not a student, you just want to, build your garage opener project. You just decide you want to do that, and you can go get these kits where some of them use those books or other sort of guide intro books, and they'll give you like an Arduino board or a Raspberry Pi and these shields, and they'll have a basic breadboard and some basic components, and usually your LEDs, so you can stick it in there and go through this process of connecting to the firmware level of the software and programming to get that light to blink on and off, which is really cool the first time somebody does that from the start to finish. And so as an introduction point, there's tons of great material and great just starter kits that give you everything you need to just dip your toes into it. And then if you do that and you're a little bit more comfortable with what you're doing, maybe you ran out and you bought a soldering iron kit now. So you can do just a little bit more than your breadboard components. You can start soldering stuff together. And, before a lot of the, you're talking about the CAD software, a lot of that CAD software is really expensive. And I think I mentioned, I think it's actually pronounced, as you said, KiCad.
KiCad, whatever. Tomato.
Potato. But it's this open source electrical PCB design software suite that is. I think I mentioned before. They got funding from CERN a few years back to essentially improve themselves, and they're at a point where it's almost as good as some of the really expensive software suites, and it costs nothing. So you can get on there, and it's one of those things where if different YouTube videos, if you ever like just browsing YouTube videos, there's some maker channels on there that go through some great introductions into okay, here's the basic setups of how to use this. Here's your first blinky light to take your blinky light off of a breadboard and produce through one of these cheap maker focused fabricator companies to actually to see something that you did on a breadboard and then actually get it built out on a PCB and get the components and solder it on there, and now you have got something that looks what 5 or 10 years ago would have essentially been a professional, board. And now you can do that, out of your garage or, your study, designing this on your computer and putting together and doing all this for, pennies on what used to be dollars, a very cheap budget. And so I think it's great because anybody that has an interest in doing this, there's not a high cost bar to getting started. Really, you just need, the motivation, to go out there and even if you don't want to, even if you can't buy the stuff, there's a lot of, open free material out there from the software side of it to, the tutorials that sort of guide new users into it. Because one of the best things about designing this kind of stuff, and this definitely applies to the software. The greatest thing about software is the flexibility, the coding. And before, the hardware was a little bit more stringent, or you need to be able to have a full lab, or you need to be able to shell out this amount of money to get stuff made. And a lot of that portion has been taken out of it. The software CAD, the CAD programs for it, there's no longer like a price bar to be able to get in there and use that and learn that. And so it's really available to pretty much anybody who has an interest in it.
It's really exciting. Well, Phil, Olivia, thank you so much for coming on the show and talking about designing electronics. I hope to have you on again very soon.
Thank you.
I appreciate it.
Thank you for listening to this episode of Planes, Trains, and Tanks. If you enjoyed this episode, please consider leaving us a review. To learn more about Shift5 and our products, visit our website at shift5.io or follow us on LinkedIn and Twitter.